गुड इवनिंग गुरुजी।
गुड इवनिंग।
गुड इवनिंग
Good
सर।
evening, sir.
गुड इवनिंग
Sir,
पीपल।
happy National Youth Day.
क्या बोल रहे हो?
So today is National Youth Day, so I am.
अच्छा, yes, happy national youth day. चलेगा, we all are youth. Yes, I'm also young, absolutely. Okay. You know, the sad part is these days, like the kids, at least in the society, who are of let's say 5, 7, 10, 12 years old, you know, running around and so like I was walking the other day and the ball passed by me and they're like, uncle, ball. Like, अरे भैया, uncle क्यों बुला रहे हो यार? But then I recall, obviously, when we were also kids, even if you're going to the grocery shop, you know, where there are people of let's say 17 years, 20 years selling things, even then we used to call them uncles. I'm like, okay, now the transition has happened, the kids can call them uncle.
Yes, sir, also we are even called.
अच्छा, है ना? Wait, I mean, as a kid also, like, even today, like, if I would see anybody elder than me whom I don't know, and if I feel that a person is even 35 or 32 or 33, let's say even if there is an age difference of 6, 7 years, I don't think I'll call my, I'll probably say uncle. Okay. So that's always there. But okay. So anyway, so do you guys have any questions until the topic that we learned yesterday? So today we have a double class, by the way. So Neeraj sir is not available in the second class, so I'm also taking the second class. But for us, we'll have 3 lectures today. Like this lecture, later second lecture, and tomorrow also we'll have. So we can take things again more, you know, nicely and in detail, and I can take more examples in the class. So that gives us more time. So that's good. Okay. So now let's start with the third kind of potential people. Please give heading. Rectangular potential barrier. Please give heading. Rectangular potential barrier. Okay. So let's define this. Again, in this also we have unsymmetric case and we have symmetric case. People, so far I have not yet taken the symmetric problems, if you realize. In the 1D box problem also we had taken the unsymmetric way, okay, and yet to take the symmetric cases. Something very beautiful happens in case of symmetric cases and hence. So right now we are still taking the unsymmetric rectangular potential barrier, okay, unsymmetric one. Okay. So how it is defined? So for example, I'll just draw the graph first, and I think I will be able to understand it better. Okay. Okay. So potential barrier, you already know, basically step potential. Even this was step potential, like ground, sudden jump, and constant. This was step potential. Rectangular means what? Means what? It will form a rectangle people. So like it will have ground initially, okay. Then there will be a sudden jump people. Initially, potential will be 0. Then there will be a sudden jump, okay, to some value v0, and then it will be constant. But it won't be constant infinitely. If it becomes infinitely constant, then it's step potential. Now it will again fall people. This time it will again fall. So it has formed a rectangle, a rectangular barrier, and then again it becomes 0. But this is unsymmetric. But this is not symmetric because on left you have 0, on right you have v0 also and 0 also. This would have become symmetric for this case. People. It would be symmetric like this. But I'm not yet taking the symmetric problems. Okay. Anyway, so now it has become 0 as you can clearly see. So we have 3 regions: region 1 this time, region 2 this time, and region 3 this time. Because so far we have taken only 2 region problems, and now for the first time we have got 3 region problems. Okay. So let's say this is our origin. This is x coordinate. Let's say this is v of x. Okay. In region 1, the value of v of x is 0. In region 2, let's say this is constant v0. Okay. So in region 2, value of v of x is v0, and in region 3, value of v of x is again 0. Let's say the rectangle has a length of 0 to a people. This length is of 0 to a. Okay. So how do we define v of x? So v of x is basically 0 for x less than a. Then there is a discontinuity. People, it suddenly jumps to v0. It jumps to v0. It remains v0 from 0 to a people. It remains v0 from 0 to a. Okay. And then there is again a discontinuity. It will suddenly fall. It will fall. And it will become a people. So it will become 0. It will again become 0, and it will remain 0 post a people. X greater than a, like a to a, 3, a, 4, a, 5, a, infinite a to infinity. It remains 0 once again. There are 3 reasons. As far as
excuse me, sir. Sir, I can imagine potential. I can think of potential as we are taking something from infinity. But how should I imagine and how should I understand potential barrier? If I'm able to take if there is a charge and if I'm able to take it from infinity in some field.
No. So it will have a constant potential for a distance. For example, if you have another charge has a field, right? And throughout this field, it has a constant potential throughout the circumference here. Let's say.
Yes.
Okay. So it's something like that. For example, charge has entered. Outside there is no potential. Again, here it doesn't have any potential. But now there is some potential in this region. 0, some potential 0. Something like that also you can think of. Okay. But provided you need to ensure that you maintain a constant potential. We don't want a varying potential. We need to maintain a constant potential.
But varying potential is also possible.
It is anything possible. But we are never taking any complicated cases in constant potential. We'll play with straight lines only. Okay.
Yes, sir.
Okay.
Sir, Vx equal to v0 and x is equal to and greater than होना चाहिए ना 0.
नहीं यहाँ पर equality नहीं लगेगा because there is discontinuity all the time. We have learned in potential there is never equality because there is discontinuity all the time.
Okay.
But as far as potential is finite, v1, v0, as far as potential is finite, wave function will be continuous. Equality you can put only for wave function. So in region 1 you have wave function psi1, in region 2 you have wave function psi2, in region 3 you have wave function psi3, and wave function will be continuous. So here only you can put equality. But potential we can never put equality. But wave function will remain continuous. So here you can put equality. We have cautiously written this the same way in earlier case also. See, by any chance if you have written something else, then that's on you. I remember very clearly that we have also written we have not put equality in potential ever, and in wave function we have always put equality. Just check if you want. Okay, yes. Everybody. And somebody was trying to ask something.
Sir, we are talking about the potential. This potential is similar to the electric potential we were discussing in electricity and magnetism.
No, it's not compulsion, and we are just saying that how can create a potential. Okay, so that's it. Potential is basically any kind of barrier that an electron can pose, or like an electron can face before it has to cross that region. For example, photoelectric effect also you have a barrier potential, a BB, that you have to cross, like work function. Okay, so that you have to cross in order to escape. So it could be anything.
So that is basically the energy.
Any kind of energy, opposition, but it is opposition.
Okay.
Faced by the electron.
Excuse me, sir. One more question, please. Suppose I'm having a sphere of radius r, and I know that the potential at the circumference is v0, and so actually and there is some like thickness dx. So at r minus dx and at r plus dx, the potential will be v0. So we should put equality in the potential case also, but we are putting in the wave function only.
No, the thing is, inside v0 it's same, but outside it's not same. Here it is v0, but who told you that here it is v0? It's not v0, it's 0 now all of a sudden. It's 0. On the left side you have 0, and then you have v0, and then you have v0 on the right side. So on the right you have v0, on the left you have 0. So no equality. Okay? Make a note, please.
Yes, sir.
And remember, people, if at all you guys are referring any book, standard books, textbooks, or anything, those people have no clue about this depth of quantum mechanics. I'm telling you that already. Many authors, scientists, or even students who have written the books, or the teachers, okay, they teach, they have the knowledge of the things as much as they have learned. They have to go deep into this to realize that where you have to put equality and where you don't have to put equality and everything. And at the same time, they think that these things are not important. Honestly, equality or not, nobody's going to ask you this. However, if I will set a paper, I will really want to ask a question related to this. Okay, like I will give you two options, like I will give you this also option, and I will give you another option where I'm putting equality. And now students will scratch your, like the students will have to scratch their head. How did this happen? How to know which one is correct? But the thing is, not many teachers are aware of these facts also. Okay. So the point is, in the books that you are referring, there could be typo error as well. Many times, the typists, they even come up with their own understanding. They think, teacher, they will think that whoever was the author,
Yes,
or they must have forgotten that to put equality here. So they would put equality by themselves. They would think that rho is like S. They would think that, okay, no, it's not rho, it's actually looking like S. So it should be S probably. These things, even the typists, they come up with their own theory in physics. Okay. But make it very clear, potential is discontinuous. If you put equality, what is the meaning of it? It has two potentials at the same point. It doesn't make sense. You cannot have two potentials at the same point. Okay. And hence we don't put equality.
Sir, Vx equals to 0 is less than 0. The first thing that's
The first one is less than
instead
0.
of
It's 0. Make it clear, people. This is your. But please keep on asking questions. It's fine. This thing needs to be clear. Okay. How this is now well clear? Let me know. I've copied this. Should I proceed?
Sir, same sign.
Yes, sir.
X is less than or equal to 0.
Yes. I mean, this is absolutely 0, people. Just make the correction. Just a second. Okay. So let's take a complicated case in this. Suppose I'm giving you there is a particle. It has energy E, but which is less than V0. Right? We're taking the case E less than V0. Okay. We're taking the case E less than V0. And now we just want to study things on this. How to find the wave function in all the different regions. Which are the wave functions that get eliminated? Maybe relationship between constants if you want to. Maybe transmission coefficient. We'll see what to do, what not to do. But important is to reach the wave function part of this. Okay. So let's do that. So first, let's talk about region 1. What's our study the equation first of all? B square psi upon dx square plus 2m upon x square into E minus B into psi. This is 0. Let's talk about region 1. Just tell me one thing. Region 1 or region 3. The idea of the derivation is going to remain same if you realize. Region 1 and region 3, both of them have same potential now. The final boundary conditions for them will be different, but initially region 1 and region 3 you can give them same atom because v of x is 0. For both of them, v of x is 0. Okay. Substitute. So what do we have? D square psi upon dx square plus 2m upon x square into E minus 0. Okay. Psi, this is 0. So what do we have? D square psi upon dx square plus 2m E upon x square into psi. This is 0. So as of now, we can solve region 1. Later I will remember that it's identical to region 3. I'll use similarity. Right now I'm just solving region 1. Okay. Later we'll use similarity. Okay. So let's put psi 1 people. I'm putting psi 1. Okay. Let's solve for region 1. So again, this is the equation which we have done n number of times solved. How do we start? We will first say like k square. K square is 2me upon x square. So what do we have? Call it k1 square now. Now you have k1 square. Okay? k1 square is 2me upon x square. So this is t square psi 1 upon dx square plus k1 square psi 1. This is 0. And we already know the answer of this. There is no need to resolve this again. What is the answer, people here? C1 e raised to I and 1x.
K1x.
And C2
Plus
e raised to
C2 e power minus I.
k1x. We have done this before. Okay. Copy this. Take your time.
Yes, sir.
Others also let me
Yes, sir.
Done, sir.
Okay. Okay. So this region is already known to us. Nothing to think about it in this. Now I will use similarly. In region 3 also nothing will change, people. You can use new constant C5 and C6. C3 C4 will use in region 2. Okay. So C5 e raised to I k1x. K1 will also be same now. Why K1 will be same? Because it will still be 2me upon x square. Because v still 0. V still be 2me upon x square. So K1 will also be 0 at K3. You cannot write K3 because K1 and K3 will be same actually. So C5 e raised to k1x plus C6 e raised to minus I k1x. This is side 3, people. How it's fine, tell me from.
So can you please repeat the reason behind K1 on both the regions?
Because both. बाप रे, ये आवाज किसका था रे?
Sorry, sir. It was background.
Okay, ठीक है.
चल गाली मत दो.
No, वैसे anyway I don't abuse, so that's not a point. But okay, proceeding ahead. What do we have? Because v of x is same in both, because v of x is same. It's 0, no? V of x is 0.
So the constant K1 also remains same.
Because tell me, is the equation same? Like no, d
No,
square
it's not. Only that side 3 is coming up. That's
only
it.
side 3 is coming up. So that's it. So the substitution of 2me upon x square that will be same now.
Okay.
So K1 and K3 are same. For your understanding, you can write it this way. Make it up, please.
Yes, sir.
Chalo, next. Let's talk about region 2. Others, let me try it. And I hope you understood why I'm not using C3, C4. I'm keeping it for region 4. Okay?
Yes, sir. Second के लिए हो जाएगा ना?
Yes. Let's talk about region 2 now. So in region 2, what do we have? First of all, P of x is V0. Secondly, we are taking a case where energy is less than V0. Okay, that's our case. So the Schrodinger equation, d square psi upon dx square plus 2m upon x square into E minus V. V is V0. Okay, E minus V0 psi. This is 0. Or psi of x, whatever we are writing. This is 0. I will be writing psi of x all the time. No, so I'll just keep it psi then. Into psi. This is 0. Okay, so this is region 3, region 2 psi 2. This is region 2 psi 2. And but the thing is, if you want, you can go ahead and write this as k2 square. But energy is less than V0. No? If energy is less than V0, then what will happen? This will be negative. K2 square will be negative. It will become complex. Propagation constant cannot be a complex number of people. So what we will do is first we will take a minus form. A very similar theory we did last time. So I'm taking minus form. 2 upon x square. V0 minus into psi 2. The only reason is they have given us V0 is greater than E. That is the case we are taking that. Okay, V0 is greater than E. So now I can take length. k2 square b 2m upon h square square into v0 minus e. And since v0 is greater than e, this is positive, so it's okay. K2 will be real. Otherwise, e minus v0 would make it negative. E is lesser, and it will become complex. K cannot be complex. Okay. So now it's real, so it's fine. So what happens to our equation? We have got d square psi 2 upon dx square minus k2 square. This whole term is k2 square, okay, into psi 2. This is 0. Copy please.
Yes, sir.
So we have got d square psi 2 minus k2 square psi 2. This is 0. So d square minus k2 square psi 2. This is 0. Okay. Psi 2 cannot be 0. D square minus k2 square will be 0. So d square is k2 square, or I can say d is plus or minus k2. We have got real and unequal roots, people. Real and unequal. So one root is k1, k2, another root is minus k2. Okay. So our solution is basically psi 2.
C3 e power k2x plus C4 e power minus k2x.
Yes. We have learned C1, C2 already. We have learned C5, C6 already. Usually we would write people C1 e raised to m1x plus C2 e raised to m2x. Like m1 and m2 are the two roots you have found out. But C1 and C2 are already used first of all. So instead of writing C1, I go with C3 e raised to m1, which is the first slope. First slope is k2 people. Okay, first root. So that's e raised to k2x plus C4 e raised to m2x. M2 is minus k2 people. Okay. So minus k2x. That's psi 2. Make note.
Done, sir.
Okay, sure. So let's write all the wave functions once again. What do we have? Psi 1 was C1 e raised to I k1x plus C2 e raised to minus I k1x. Psi 2 was C3 e raised to k2x plus C4 e raised to minus k2x. And psi 3 is C5 e raised to I k1x plus C6 e raised to minus I k1x. Now listen, you don't have to tell me the answer. I'm giving you 1-2 minutes. Think about it. Write it in your notebook. Don't tell me the answer. Write it in your notebook. Which of the terms are becoming 0? Don't tell me. This is just for yourself. Take 2 minutes. Don't tell me the answer. Just keep it in your notebook. Which are the terms becoming 0? Because if you are able to do this, it means I can be least worried about the wave function type of problems. The concept is completely hammered in your head. And one of the most confusing concepts we have very soon in the class. Take your time. I'm just waiting for the time to become 28. You know, there is an interesting feature here which I'm not used.
28.
It has become 28. Okay, this time I'll just show you that feature. Where is it? Features, I think applications and stopwatch. Have a look. As you can see, there is a stopwatch, so I can like start the countdown here. Let's say maybe 1 minute here, and I can start. And I will just now wait. Interesting, no? This software provides many interesting options. But okay, chalo. Let's continue. Hang on. What happened?
Countdown is happening, sir.
It's not that the mouse is not working. This is it. Now it's working. So let's calculate this. Understand. So first of all, this is complex. This is complex. You can apply the idea of propagation. People, e raised to I k. This is plane wave equation. So this is positive. It means moving in the forward direction. This is negative. It means it is moving in the backward direction. So when you talk about psi 1, is both possible or not? Let's check. In reason 1. So positive is incident. Negative reflection. Very much possible. Classical and quantum both allows reflection. In fact, here e is less than v0 now. So both will allow reflection. So here I can simply say this is incident. Okay, and this is reflection action. Anybody has any doubt? You can ask right now. Next. Now let's talk about this. So here, as we understand, it's real people. You cannot use incident reflection concept now. You cannot use propagation concept because the plane wave equation must have ikx. Because it does not have ikx, I cannot use propagation concept. We have to use the boundary condition concept this time. Okay. Now the thing is, people, region 2 is actually valid only from 0 to a. It's not 0 to infinity. By any chance, if you have used infinity, that would be wrong because it's only from 0 to a. Because it's 0 to a. Is 0 affecting my calculation? No. 0. If you put 0, e raised to 0 is 1. E raised to 0 is 1. Even if you put a, is it affecting your calculation? No, people. This time the whole term is your wave function in region 2. You can call it refraction term, or you can call it whatever term you want, transmission, whatever you want to call it. This whole term is a wave function in region 2 people. Okay, cool. Nothing changes now because this time x is valid between a and 0. So lowest is even, highest is a this time. It's not infinite this time. So it's not becoming infinite from 0 to a. It's not becoming infinite. Okay. Next, however, here again you have got this plane wave equation ikx minus ikx. So this means forward and this would mean backward. What is the meaning of forward in region 3? In region 3, forward only means transmission is happening. Now listen, the thing is, classical mechanics will prohibit transmission because energy is less than v0. But quantum mechanics tells us that there has to be some probability of transmission. We learned that the probability is decaying people. But it may decay, but it can still be transmitted. Okay, it may decay people exponentially, but it can still be transmitted. Okay. So the point is transmission is very much possible. So yes, it can move in the forward direction. But backward direction region 3 doesn't make sense to us. What is this? Useless. So backward direction is not making any sense to us. So what we can say is this is fine. This tells us information about the transmission. This doesn't exist. So the only constant that is becoming 0 here is C6. And if you're able to do this, pat your back.
Yes, sir.
Good. Okay. Because main was this actually. Main was this idea that here none of them is becoming 0 this time. Because it's 0 to a, it's not 0 to infinity. Okay. Make a note, please. Ask me if you have any questions. Good. So this is incident, this is reflection, this is final transmission. This is something that is happening in between, intermediate process.
Excuse me, sir.
Haan ji, bolo.
Sir, can theta be imaginary?
Can theta be imaginary? I have not learned angle to be imaginary, to be honest. But why?
I have also not. Sir, if we took, I mean, अगर आप दूसरे केस में 2m by h square square और e minus v0 को अगर k2 लेते हैं,
हाँ,
तो हमारे पास जो मतलब आंसर आता है ना साइड 2 का वो आता है c1 e iota bracket minus iota k2. प्लस
Okay.
सी टू आयोटा इंटू आयोटा के टू। अगर मैं आयोटा मतलब माइनस आयोटा के वन माइनस आयोटा के टू को मैं थीटा लेकर चलूं तो वो उसके ब्रैकेट में फिर ऐसे आएगा ना कोस माइनस आयोटा के टू, इसलिए मैंने पूछा।
Okay, नहीं, we cannot do that. And also the thing is, क्योंकि आपने e minus v naught लेके चला है, that is why first of all we are going on immediately, because if you are writing this as k2, if you are writing this as k2, then k2 is becoming imaginary. K2's wavelength is becoming imaginary.
Yes sir.
So that's not possible. Hence,
Yes, sir.
we can never write this as k2. Okay,
Yes,
okay, no problem.
So I'm going from one thing to another thing. I was just trying with my
I
pencil.
understood. That's fine. I mean, it's always a curiosity. What would have happened if we would have done that? So it's okay, you can ask what if questions all the time. No problem. Chalo. Okay, so this is done. After this, we have got people. This time we have got 5 constants. Okay. See, earlier we used to have only 3 constants: C1, C2, C3, C1, C2, C4, and we had 2 boundary conditions. So we had 3 constants and 2 boundary conditions. What we used to do? We used to write C3 in terms of C1, C2 also in terms of C1, and then things used to get cancelled by taking ratio. Now C3 upon C1 was getting cancelled, C2 upon C1 was getting cancelled, and we used to have some values. So the point is, if you have 3 constants, I must have 2 equations. If you have 4 constants, I must have 3 equations. If I have 5 constants, I must have 4 equations this time. I hope first you're getting this. Write it if you want. But previously isn't before this example's case, people, we used to have 3 constants and 2 equations. And what we used to do was we used to express C3 as a function of C1 and we used to express C2 as a function of C1. Okay, so that was done and ratio was taken and things used to get cancelled and we were done always. But now that if we have 4 constants, it means I must have 3 equations now so that I can express C2, C3, and C4 in terms of C1, people. And if you have got 5 constants, then I must have 4 equations so that I can express C2, C3, C4, C5, all of them in terms of C1, people. I need 4 equations now. How can I get 4 equations? That's the next question.
2 can be from continuous wave function,
Hmm.
another 2 from the derivative.
Okay. Basically, we have 2 boundaries this time. We don't have 1 boundary. One boundary is between 1 and 2, another boundary is between 2 and 3 people. That's it. Okay. But never equate 1 and 3 in hesitation, I mean in haste or whatever. There is boundary condition between which 2 points, people. Region 1 and region 2 are sharing a boundary at x equals to 0, and region 2 and region 3 are sharing a boundary at x equals to a. Okay. So write it in English if you want. First, I hope you have written this. Write this. So all you have to do is we have to express 5 constants like C2, C3, C4, C5 in terms of C1. We will express C2, C3, C4, C5 in terms of C. And we're not going to do this calculation in the class. I'll just give the boundary conditions and then we'll stop. Because in Java MCQs, at maximum, what they can ask is find the wave function, okay, or find relationship between constants. In the TIFR paper also that happened this year, there was a question related to wave function. People, they had given a random potential. Now that you know how to do, so those who gave TIFR, you have received a solution like paper response of yours. So just check the paper response, check that question, and try to attempt that question. Now, all you have to do is find the wave function, I think, in different regions. Okay, so done, people. Let me write it. Okay, so let's write it clearly. Psi1 and Psi2 share boundary at x equals to 0. So their boundary conditions can apply, and Psi2 and Psi3, okay, share boundary at x equals to a, people. Okay, so basically we have got 4 equations. That's it. The first equation would be find Psi1 at x equals to 0, equate it with Psi2 at x equals to 0. Second equation would be find derivative of Psi1, then substitute x equals to 0, equate it with derivative of Psi2, and substitute x equals to 0. Third equation. Okay, Psi1 and Psi2 are done. Now let's talk about Psi2 and Psi3. Again, find Psi2 at x equals to a and equate it with Psi3 at x equals to a, people. And fourth equation would be find derivative of Psi3. Okay, put x equals to a. Sorry, derivative of Psi2 and put x equals to a, and equate it with derivative of Psi3 and put x equals to a, people. This is how we will have 4 equations. And then you know this way. After this, all that you do is once you have got the relationship C2 in terms of C1, C3 in terms of C2, C3 in terms of C2, C3, C4, C5, all of them in terms of C1. Once you have got that, what you will do is you will calculate a wave function like JR, people. JR of Psi I, JR of Psi R, JR of Psi T. And once you have calculated JR of Psi R, and Psi T, you will calculate R and T. You know how to calculate R, mod of JR upon mod of JI, and how to calculate T, mod of JT upon mod of JI, people. So the process remains the same, but it's a tedious process. We are not taking those processes anymore. Okay? We'll just reach the final result now. Copy this much. Writing. Next. Clear? Let me know if you want to ask anything there to me right now. If you have any questions in your head. I hope you understood the process. Process remains the same, but it's a tedious process, so no more derivation. Okay. Sure. So people at the very end, what is the suggestion by the way? You don't have to calculate everything. Like you can calculate C2 in terms of C1. That's fine. Okay. There is no need to calculate C3. There is no need to calculate C4. Just calculate C5, people. Just calculate C5 in terms of C1 because C5 is a transmission. Tell me one thing. C2 is reflection, and C5 is transmission. We don't care about C3, C4 actually. Honestly, we don't care about C3, C4. That is a refraction term that is happening in between. So just get C2 in terms of C1 and C5 in terms of C1. Once you are done with that, you will calculate the respective GI. Sorry, first GI using h square upon 2i and psi star del psi minus psi del psi star. Then you will calculate GR. Then you will calculate JT, and then you will calculate R, which will be magnitude of JR upon JI, and you will calculate T, which will be magnitude of JT upon JI. But here also we can be a bit smart, people. Instead of doing so much, we can do just one thing. Don't calculate so much. Just calculate GI, calculate JT. Okay, calculate transmission coefficient, which is JT upon JI. Once you are done with this, what's next? Can I write R as 1 minus T? Done now. R plus T is 1. That condition can still use an R will be 1 minus T. Okay, make a note.
So we are ignoring totally the absorption.
But no, actually, okay, no, that's a good point now because there could be a chance that the probability. Okay, no, that's the point. That's a valid, absolutely legit point because it is going to decay here and then it will be transmitted. So yes, it will actually depend on this width. So it will depend on skin depth. So if you calculate skin depth, if it is greater than 8, then transmission won't be possibility, and if it is less than 8, then yes, transmission is a possibility. Okay, so no, good, Sanju. No, so I think we will have to go with the usual method. Okay, leave it. So the usual method only. So we'll just calculate R and we will calculate T, and can calculate absorption also this time. Absorption is not absorption, but basically the probability that the particle will be refracted, but it won't be completely transmitted. Like R plus T now cannot actually be 1, because there is some probability this time that the barrier itself will absorb the wave this time. There is a way to do it now. So what can happen is refraction happened, it was transmitted into the region 2, but it decayed, and maybe it just stopped. It couldn't exceed region 3. That is something that can also happen. So yes, that's a legit point. Okay, so that's it then. I mean, it's not that we don't have to write C2, C5, we'll have to calculate everything this time. Hang on. Just a second. So actually we'll have to calculate everything. So don't write any of this. Don't write any of this. So the last thing, correctly written is only this. You will have to calculate C2, C3, C4, C5, all of it. You will have to calculate all the GR, GT, GI. Also absorption part also you can calculate. You can calculate the amount that could be absorbed maybe and which could not be transmitted. Anyway, out of all of this, there is only one formula which I want you to by heart. Just one formula. People, the transmission coefficient comes out to be. The transmission coefficient comes out to be, because this is something which classical prohibits, but quantum has allowed. Okay, so transmission coefficient comes out to be approximately. Okay. Otherwise, there is a whole lengthy formula of this. It's approximately equal to, I just need you to remember, a e raised to minus 2k2a. I'll tell you the meaning of all the terms, don't worry. First, you need to remember this. Remember, only quantum allows this. Classically, t should be 0. T is 0 classically, okay? Because e was less than e0, it should not be transmitted. But quantum tells us that there is some probability that it will be transmitted. So what is a? A is a constant, a very bad constant, because it's a very lengthy constant. Okay. So the constant of a is given by, again, this is an approximated constant of a, okay? The approximated constant of a, which is 16 into v0 minus e into e, the whole upon v0 square. v0 square. You know the value of v0, you know the value of e, you know the condition that v0 is greater than. So this is the value of e, okay? 16 into v0 minus e into e upon v0 square. See, we have to by heart these things because obviously we are not deriving these things, and in exam also you won't have time to derive these things. So there is no option other than by heart. Okay? So t is a raised to minus 2k2, and a is basically this kind of constant. K2 you already know. What is K2, people? K2 is under root of 2m into v0 minus e, 2m into v0 minus e upon x square. That was K2 square now. So I just take a square on that x value. K2 square was 2m upon x square into v0 minus e. Okay? So K2 we already know. And small a is the width of the rectangular barrier. Small a is width of rectangular barrier. So that you have already seen. Make a note, please. Just one formula that I wanted to by heart. Nothing else. They won't ask anything else. Ask me if you have any questions, don't hesitate. Done, people?
Yes, sir.
Sure. Okay. Also, I need you to note it right now before things change and before you proceed. People, this formula of transmission coefficient will be same also for symmetric rectangular barrier, right? The formula remains same for symmetric potential barrier. So even if I would have given you a potential barrier like this, okay, but listen, okay, it's same if you realize v of x is 0, v of x is 0, and v of x has become v0. But the way you write these things, that changes. Like for example, width has to remain a, width cannot change now. Width has to remain a, but the coordinates have changed now. This is 0 now, this is minus a by 2 people, and now this will be k by 2. So as far as the width is same, transmission will remain same. So the transmission coefficient here also is a raised to minus 2 k2 x p2. Here also it is the same stuff. Okay, minus k2 a. As far as width is same, okay, the formula will not change. Right, it is same for symmetric potential barrier as well. Symmetric rectangular potential barrier as well. Okay. So now, why the symmetric cases are actually more interesting? Now we will take a case so that you understand that why these cases are more interesting and why we have been avoiding to do those so far. Done, people? Sure. Next. But remember one thing very clearly, that this width should remain same. As far as a is same, formula remains same. If a changes, suppose by any chance they're writing minus a to a, don't use this formula. You'll have to make a change. What will be the change this time, people?
2a.
Replace a with 2a, because this is minus a to a, so this becomes 2a. So here a you have to replace it with 2a, so total becomes 4a in that case. So you have to make those appropriate changes. Write it if you want again. Write this also. So appropriate changes you have to take care of.
So can you please repeat?
So initially you had minus a by 2 to a by 2 now. So width was a. So the formula is basically e raised to minus 2k into width, whatever is the width. But if minus a by 2 to a by 2, instead of that we write minus a to a. Transmission coefficient cannot be minus 2k. Now what is the width? Width is 2a, correct? A on left side, a on right side. E is 2a. Width is 2a. Since width is 2a, it's minus 2k2 into width. So width becomes 2a. So 2 into 2, that becomes 4 now. Clear?
Yes, sir.
So it's basically a raised to minus 2k2 into width. Then whatever is the width you have to take care of. Thus. And it's an approximated formula. The original formula is a very large one which has 3-4 terms under the roots. And you are not supposed to by heart that, so don't worry. But please by heart the coefficient a. That's important. That it is 16 v0 minus into e upon v0 square. Okay? Next. Let's take symmetric 1D box now. Please give it. Symmetric 1D box. Okay. Or basically symmetric infinite potential. 1D box by default is actually the unsymmetric one. So I would like to call it symmetric infinite potential. Okay. Or if by any chance they write, then they have to make it very specific symmetric 1D box. Remember, 1D box by default case, that is actually unsymmetric one. Okay. So how does the potential look like now? We have got v of x and v of x. How did we use to write 1D box? Something like this, and we used to go until infinity now. But now we have to just actually make it symmetric. So let's make it symmetric along y axis. So this is infinity. V of x, this is infinity. Okay. Here also we have got V of x, and that is infinity. Okay. And between we have got V of x, and that is 0. Width has to remain a people, or L. I think we have been using L all the time for multi box, right? Root of 2 pi x sin n pi x by L. So I'm going with L. Width has to remain L. So LHS will be minus L by 2. This is 0, and this RHS will be L by 2. Just in case you write minus L to L people, a lot will change in your formula, because in that case length becomes 12. If you write minus L to L, okay, take care of that too. So one thing that again I have taught you, and I think some of you remember that thing, and I hope that you remember it. People, that was theorem related to symmetric potential. As far as the potential is symmetric, what do you know about the wave function?
Wave function is always continuous.
No, it may be symmetric or antisymmetric.
Yes, it may be symmetric or antisymmetric, but it has to be either of them. It has to be symmetric or it has to be antisymmetric. It cannot be a random wave function. See, Rita, what you told, that was if potential is finite, then wave function must be continuous. That's different. Finite potential and continuous wave function. Now we are speaking about if potential is symmetric, then the wave function is either symmetric or antisymmetric, and we created a very beautiful flowchart also related to that. It's either symmetric or antisymmetric. It has to be either of them. Okay.
Yes, sir.
So write it right now first of all. Please write. Since wave function is symmetric now, so since potential V of x is symmetric, okay, the wave function, must be either symmetric or antisymmetric. Okay, must be either symmetric or antisymmetric. So now how this changes the whole thing that we learned in the original 1D box people. That's very interesting to learn. Okay, let's go ahead. And somebody had asked me a question also related to this, and I told you that when we learn it, let me know. So once we're done with that topic, if you have that question, we can still solve it. But let's complete this first. Okay.
Excuse me, sir.
हाँ जी बोलो.
सर एक क्वेश्चन है ये आपने कैसे पता कि Vx is symmetric? Just to please elaborate.
So okay, what is the meaning of symmetric wave function? That V of x has to be equal to
V of minus x.
So tell me one thing. When x is positive, what is the value of V of x?
0.
When x is negative, what is the value of V of x?
0.
When x is L by 2, what is V of x?
Infinity.
And when x is minus L by 2, what is V of x?
Minus me.
Infinity.
Oh,
Infinity. It's
okay.
same. It's same. You know? You can write since V of x is equal to V of 1. Whatever is on the right side, exact symmetricity is on the left side. You call it symmetric. Right? Write this. Whatever is on the right is exact that we have on the left. That's why you call cos also symmetric. Now, why cos is symmetric people? Because whatever you have right, exactly ditto you have on the left people. Cos is mirror image. So cosine is a symmetric graph. It's an even function. Symmetric means even now. So cos is even function because whatever you have on the right, same you have on the left. Okay. Symmetric means second and first quadrant are equal. Antisymmetric means first and third quadrant are equal. For example, sine. Sine is antisymmetric. Sine is odd. Why? Whatever is on the first quadrant, reciprocal, it has to start from third quadrant. Like this. It starts from third quadrant. Like symmetricity goes like this people. When it is antisymmetric, sine, antisymmetric or odd. Okay. These things actually. Okay. I'm actually this would be a long diversion then. So let's see. If tomorrow we have time, then remind me about symmetric and antisymmetric. I will also connect these things to Fourier series. Have you learned Fourier sine series, Fourier cos series?
Yes, sir.
So
Yes,
that's,
sir.
that's it now. So that these things are similar there. How do you make a Fourier sine series? You need to make it to have sine. What do we make it? Bn sine n x now. So a naught will be 0 and ab will be 0. We make it odd.
Sir, बता देना class में.
So basically you have to make it odd. In order for a Fourier sine series, you have to make the function odd. You have to make it antisymmetric. And for Fourier cos series, you have to make it symmetric actually. But okay, remind me tomorrow. I will connect it to that. Not now.
So please go back to the first last page. I want to ask something.
हाँ.
So what do you denote by dotted line? That dotted lines.
ये infinity के साथ है मतलब obviously. It's undotted means it's like a rigid boundary. Like just like in classical mechanics you draw a rigid surface, no? It means nothing can pass through. It means wave function, like it cannot pass through because wave function is not defined when potential becomes infinity, no? So now potential on the complete RHS is infinity. Wave function is not defined here. Psi of x is 0. It does not exist basically. It becomes 0 on right side. Okay. So if you want, you can write psi of x also. I hope you understood a couple of things at least, that this is symmetric and why it is symmetric. I hope you understood. Tell me if not right now.
Yes, sir. समझ गए.
And if you want to study wave function is 0 on x less than minus a by 2, and there has to be equality. Wave function is continuous, okay? And then hang on. Wave function becomes, let's say psi. It becomes psi between minus a by 2 and a by 2. It becomes psi between minus a by 2 and a by 2. And again it becomes 0 for greater than a by 2. Make a note.
Yes, sir.
Okay. Sure. Next, I hope you copied this.
So one thing I
Sir,
want to
one
tell you.
हाँ पूछो ना बोलो.
So psi equals to 0 and psi equals to infinity. What is the meaning? Difference, significance, please elaborate something.
Psi equals to infinity. It means it doesn't make sense. It doesn't make sense.
Okay, okay.
हाँ, psi equals to 0. It means it does not exist.
There is no probability to find particle. That means.
हाँ, psi is 0, so probability density is also. It means there is no like wave function could travel in the region, but probability of finding the particle can become 0. But when something becomes infinity, it means it doesn't make sense. So it's not defined. You cannot define it.
Okay.
No problem. Chalo, let's continue. हाँ, let's proceed. If you want, you can write what we do. What do we have? Just a minute. Okay, so there is only one region basically this time. Here it is already 0. We just have one region equal. So let's solve for this region. Okay, the middle region. So what is our Schrodinger wave equation? D square psi upon dx square plus 2m upon h square into e minus b psi. E minus b psi. This is 0. But v is 0 people. V is 0 between minus a by 2, x and a by 2. Okay, so what do we have? D square psi upon dx square plus 2m upon h square into e minus v. V is 0 into psi. This is 0. So d square psi upon dx square plus 2me upon h square into psi. This is 0. You know what to do here? You just put this as k square. So let k square be 2me upon h square. No problem. So let's have a k square. So again, what do we have properties for that? We have done this a number of times, and we know the final answer already. Okay. But this time we'll not write e raised to kx wala formula. We'll write cosine wala formula because in 1D box we use cos and sine. We used to write e raised to ikx so that we wanted to identify the direction. Here there is no direction. There is only one region. Left it doesn't exist. Right it doesn't exist. It exists in between. So we don't care about the direction now. Okay. We'll write
Yes.
this in the cosine terms. Okay. So what do we have? D square plus k square into psi. This is 0. So d square is minus k square, or I can say d is plus or minus under root of minus t square, or I can say d is plus or minus under root of minus 1 into under root of k square. So d is plus or minus I k. So this is comparable to alpha plus or minus I beta b. Okay. So I realize alpha is 0 and beta is k. This time I'm not going to use that e raised to I k x for the formula, people. I'm going with e raised to alpha x into c1 cos beta x plus c2 sin beta x. So we have got e raised to 0x into c1 cos kx plus c2 sin kx. So the wave function side is c1 cos kx plus c2 sin kx. And here onwards, the difference between 1D unsymmetric box and 1D symmetric box starts. Here onwards everything is symmetrical. Until here, until here things were same. First you copy, then I will save it. Copy.
This is the wave function of the particle.
In the box,
Free particle. Okay.
Free particle, because we have resistance. So yes, this is the wave function of the particle inside the box.
Done, sir.
Okay. Anybody let me try in? Okay. Now listen, people, when we did 1D unsymmetric box, 1D box, the regular one, we used the same process and we had reached the same step. After this, we had applied boundary conditions there, if you remember. Okay. And we found out C1, we found out C2. I think we had found out that C1 was 0. We ended up with C2, and we found out C2 using normalization, if you remember. When we got psi was root of 2 by L sin n by x by L. That is how we proceeded in that box wala problem. However, here what we are supposed to do is very interesting. Okay. There are two cases. One is wave function will be either symmetric or it will be antisymmetric. Okay. So let's start. Case 1. When wave function is symmetric. People, symmetric means what? Even. Even means which wave function? Sine or cos?
Cos.
Cos is even. It means sine term cannot exist. Okay. Sine cannot exist.
C2 equal to 0.
C2 is 0. What is wave function this time? It is just and just c1 cos kx. C1 cos kx. And using normalization, we know we will get the value of c1 to be root of t by l. So you can anyway use normalization formula psi star psi dx equals to 1. This time it goes from minus a by 2 to a by 2. Okay? This time it goes from minus a by 2 to a by 2. And you get the answer. Using this, you get the answer of c1 will be under root of 2 pi. I think I'm writing L, right? See, I'm writing A half of the time. I'm writing L half of the time. I hope it's understood.
Yes,
I'm
sir.
writing A here, but it is L. Okay.
Yes, how we wrote that.
But it's fine. A L whatever. Okay. So root of 2 by A sin n by x by e. Or if I write L then L half. Okay. So C1, no, sorry, C1 will be just root of 2 by. Okay. C1 will be just root of 2 by. You can solve this. We have done many questions on normalizations. For your time pass efforts, you can please solve this later. Okay. So C1 will be root of 2 by A. And let me think something. I'm thinking. So the wave function psi becomes root of 2 by A cos kx. Okay. But the question right now is you want to study the value of k also. This one. Okay, so it's fine now. Okay, so now we want to understand if C2 is 0, let's use this condition. Since C2 is 0, it means I'm thinking, still thinking. C2 sin kx, should I put C2 sin kx as 0? Okay, wait. So what we can do rather here is or I can also say sin kx is 0. And C2 is 0 or sin kx is also 0. That's also fine. Let's write or sin kx is 0. And sin can take 0 value. Sin can take 0 value. Write this. C2 is 0, or I can also say sin kx is 0. Let's use this. Okay. So what do we have, people? Since kx will be 0, because it has to be symmetric wave function. For symmetric, only cos has to exist. It means sin cannot exist. Since I've written sin cannot exist, let's rather, instead of writing C2 as 0, let's write sin kx is 0, because I can find the value of k from that. Okay. So this becomes sin kx will be, when does this become 0, people? Sin becomes 0, sin 0 is 0, then
N pi.
sin pi, right? 2 pi, 3 pi, and it goes on. So it becomes 0 at sin n pi. Sin n pi. Okay, so this is sin kx. I'm still somewhat confused because
Sir, k equal to n pi by x आता हो गया?
that's not a problem. So k is n pi by x, that's not a problem. So that's n pi by x actually I'm getting. I need to check a couple of things now. It's n pi by x. If you substitute that here, we are being misleaded right now. Just a second. I'm not using boundary conditions. Give me just 1 minute.
X equal to plus minus L by 2 पर sin 0 है ना, तो आप उस बाउंड्री कंडीशन से आएगा कि
No, I'm not using boundary conditions. That's what I'm saying right now. Hang on. So wave function we have got, and then for odd parity, it has to be a function of sin. For even, it has to be a function of cos. Okay, so I don't care what they have done. Leave it. We will use boundary conditions. People, I hate this. At the end, what I want is what I want. Let's do one thing.
So
okay,
C2 is 0.
So C2 is 0. Well, let's use this one.
So
Well, that's what we have.
what are you thinking? That
No, I need to get a result, and that result usually students think that it's a wrong result, but that's a correct result. You know what is the result? In even parity, like for cos, when you say even, the quantum numbers that are valid are only odd ones, 1, 3, 5, 7. In odd parity, that is the sign one, the quantum number that are valid are even numbers. It's actually the other way around. So that's what I'm trying to get here. But we will get it if we let's go with our method. I don't care what they have done. People C2 has to be 0. We know this now. Let's do this. So we have got so far what psi is root of 2 by cos kx. So that's fine. Or C1 cos kx, anything is fine. Even normalization, I mean, even though we have used normalization, that's fine. So psi C1 cos kx doesn't matter. Let's use boundary condition. Let's use any boundary condition. Which boundary? Wave function is becoming 0 at a by 2. Let's use that. Okay. Wave function is 0 at x equals to a by 2. है ना? देखो. Correct?
Yes, sir.
At a by 2 or l by 2, whatever you're writing, wave function has to become 0 people. Okay. So I'm using that boundary condition. Please tell me if you have any confusion. Don't hesitate. Tell me right now. So 0 is C1 cos of k into x. That is a by 2. Good. So 0 is cos k a by 2. Outstanding. We will get the result now. Many times we should use our own head. What is 0 people by the way? When do we get 0 in cos? Cos pi by 2 is 0.
2n plus 1 pi by
3 pi by 2 is 0. 5 pi by 2 is 0. Basically, absolutely multiples of pi by 2 is 0. You can simply say cos of odd multiple of pi by 2 is 0. So yes, odd you can always write 2 into n plus 1. Okay, you can always use this. And if your n is starting from 0, I think we want to use quantum number of boxes. In boxes,
n should be equal to 1.
Yes,
n1 should be
yes. And if n will start from 1, then you cannot use 2n plus 1.
2n minus 1.
Yes. Now we have to use 2n minus 1. Okay, for others, I will just explain this thing. This is a very important concept where, see, when n starts from 0 now, 0, 1, 2, 3. Okay, what is 2n? That's even number. That's 0, 2, 4, 6. That's fine. And how do we get the odd numbers? 1, 3, 5. If you add plus 1, if you add plus 1, so 0 plus 1 that's 1, 2 plus 1 is 3, 4 plus 1 is 5, 6 plus 1 is 7, and it goes on. This is how we get odd. But if n starts from 1, then even is still 2n, no problem. Even is still 2n, which is 2, 4, 6, 8, it is still 2n. But if you write 2n plus 1, you know what will happen? 2 plus 1, you will get 3, you will get 5, you will get 7, but there is 1. You miss out on 1 now. You have a 2, 3, 4, 5, 6, 7. And hence what we do is we use 2n minus 1. Because what if you use 2n minus 1? 2 minus 1 is 1, 4 minus 1 is 3, 6 minus 1 is 5, 8 minus 1 is 7. Now we get all the odd numbers. So if n starts from 1, you have to use 2n minus 1 for odd. And if n starts from 0, then you have to use 2n plus 1 for odd. First, you copy this above margin. And tell me if you have any questions. Don't hesitate, please.
Yes, sir.
Chalo. So now that we have got odd multiple of pi by 2, and because we know in box our n starts from 1, you have to use 2n minus 1 times pi by 2. I hope all of you understood why 2n minus 1. Okay, cos gets cancelled. So ka by 2, it will be 2n minus 1 into pi by 2, which is odd multiple. You can write odd word also, doesn't matter. Okay, so 2 gets cancelled. You have got the value of k people. What is the value of k? Copy this first. And please tell me if you have questions. I hope there is no confusion. We have just applied boundary conditions. Nothing else we have done. It's a regular problem. The only thing we have done differently this time is after getting this step, we are doing a case where wave function is symmetric. It means sine cannot exist. C2 should be 0, and psi will be C1 cos x. C1 you can find, that's fine, root of 2 by 8, that you will always get. I'm now using I'm now using boundary conditions. Sine is C1 cos kx, and using boundary conditions, I'm trying to do something here. Using boundary conditions. Okay. Sanju, you were saying something.
So why are we not taking n equals to 0 here?
No, because quantum in Monday box we have used now n is 1, 2, 3, 4. So we want to keep it that way. Otherwise, if n becomes 0, energy, ground state energy will become 0. We know that ground state energy cannot be 0. It must have some value even in ground state. Okay. No problem. Okay, so what's next? So Ka is 2n minus 1 into pi. Okay. Ka is 2n minus 1 into pi. It means we have found out k, which is 2n minus 1 into pi by a. And 2n minus 1 is odd now. People, it's odd pi by a. What have you got? Basically 1 pi by a, then 2 pi by a, then sorry, odd means 1 pi by a, then 3 pi by a, then 5 pi by a. People, like I said, what are the quantum numbers that are valid this time? And when you write n pi by a, only odd values are valid. When it is valid? When are you using odd numbers? For even case. That's what I'm trying to get all the time. When the wave function is symmetric, when the wave function is even, the quantum numbers are odd. So this is the most beautiful thing about symmetric wave potentials. Okay. First write this and then we'll go proceed ahead. Like this. So right.
A is the quantum number.
Not A, 135. That is quantum number. 2n minus 1. 135 is quantum number.
Okay.
I should do one thing because you mentioned that. Let's just write this as 2p minus 1 right now. Please make it 2p everywhere. I want us to use n as quantum. So make it 2p, all of you. Okay. So here also this will become 2p, 2p. Okay. So 2p minus 1 is 135 right now. 2p minus 1 that we have is 135. So what are the possible wave functions, people, now? So here we have found out, no? So what is psi? So the anti-symmetric wave function, we are learning symmetric wave function now. So the symmetric wave function, people, is psi is root of 2 by a cos ka. Have you root of 2 by a cos kx, not ka, sorry. Root of 2 by a cos kx, that was our psi, people. Symmetric wave function, root of 2 by a cos kx. Okay. So what are the possible values now? So people, psi 1 is a possibility where you have root of 2 by a. What will be k in that case? 1 pi by a into x. Then you have psi 3 as possibility. What do we have after that? Root of 2 by a cos of 3 pi by a is the next possibility. No? Because k can take 1 pi by a, k can take 3 pi by a, k can take 5 pi by a, 7 pi by a, 9 pi by a. Okay? So psi 5 is possibility. Root of 2 by a cos 5 pi by a x dt. Psi 1, psi 3, psi 5 are symmetric wave functions with odd numbers 1, 3, 5. So this is cos of n pi x pi kind of stuff only. It is cos of n pi x pi a only. But n takes only 1, 3, 5. Any doubts, anyone until here? Do you want 2 minutes to process this, to go through this again?
I got this much.
Okay. So let's take anti-symmetric wave function. I hope you have copied this, okay? Now let's take anti-symmetric. Don't worry, at the very end I will give you a conclusion also, like the whole gist of it, like a flowchart. Okay. So let's talk about anti-symmetric wave function. So please give it. But now you should know the process of this. When you say anti-symmetric wave function, it means odd wave function. Okay. Our wave function that we had got was C1 cos kx plus C2 sin kx. But when you say odd, it means only sin can exist. Cos cannot exist now. Cos cannot exist. Okay. So C1 has to become 0. This term has to become 0. Odd cos is an even function. Okay. So psi of x is just C2 sin kx. And eventually we found out C2 was like root of 2 by x. That's sin cos. Root of 2 by sin kx. I hope you have it. This is when the wave function is anti-symmetric. Tell me if you have any questions. Don't hesitate. Okay.
Yes,
Why cos cannot exist? Because it's odd. Okay. Cos is even. Chalo, next. Now let's again put boundary conditions. So again I will say psi of x becomes 0 at x equals to a by 2. Let's use that. Okay. So LHS, psi of x becomes 0, root of 2 by a, sine of what do we have? Kx. So this is k into a by 2. Huh? I just put the condition. People tell me if you don't understand this. Psi of x is 0, root of 2 by sine kx is a by 2 plus. Okay. So 0 is sine k a by 2. Okay. When does sine become 0 now? So sine k a by 2. This is equal. So sine becomes 0 at 0, pi, 2 pi, 3 pi, and goes on. Okay. But again, we will not take 0 as a value. You know why? Because we cannot have 0 quantum number people. So we can have pi, 2 pi, 3 pi. We'll take those values. Let's call it sine p pi once again. Where p is 1, 2, 3, 4, 5. P is again 1, 2, 3, 4, 5. Okay. P pi. Okay. So what do we have? Compare k a by 2 is p pi. What do we have? K is 2p into pi by a. 2p means what? Even. 2p means
Always even.
even. It means for odd wave function, for antisymmetric wave function, quantum numbers are only even. N pi by a. Quantum numbers are only even. For odd wave functions, for antisymmetric wave functions, quantum numbers are only even. So k can take only which values? It can take 2 pi by a, it can take 4 pi by a, it can take 6 pi by a, and it goes on. Okay. Okay, next. I hope you have copied this. So just like last time we have written for symmetric wave function, what happens for anti-symmetric wave function? Okay, the wave function becomes root of 2 by a sine kx, but k can take only even values people this time. Here k could have taken odd values of pi by a, but here k takes only even values of pi by a. It means I can only have psi 2, which is root of 2 by a sine 2 pi x by a. I can have psi 4, which is root of 2 by a sine 4 pi x by a. I can have psi 6, which is root of 2 by a sine 6 pi x by a people. Psi 1 has cos, but psi 2 has sine. Psi 3 has cos, but psi 4 has sine. Psi 5 has cos, but psi 6 has sine. This is the difference between infinite 1D box and unsymmetric 1D box or symmetric 1D box. Because in infinite 1D box, what was the formula? It was always root of 2 by a sine n pi x by a. Always. Psi 1, what was psi 1? Root of 2 by a sine n 1 pi x by a. Psi 2 was root of 2 by a sine 2 pi x by a. Psi 3 was root of 2 by a sine 3 pi x by a. It was always that. But in symmetric, 1 is cos, 2 is sine, 3 is cos, 4 is sine, 5 is cos, 6 is sine. This is the difference between unsymmetric and symmetric. That's it. Okay.
Sir, I have a request. Can you keep that? Can you stop the class at sub 30 because I am getting out of charges in my mobile?
Can we stop the class at 7?
Sub 30. That means 6:30.
6:30 only. Okay.
Because I am getting out of charge. Yeah.
Sure. Okay, yes, sure. But,
Discuss between how much.
yes, absolutely, no problem. And we have done this. I just want to conclude this now.
So
Done this. I think it's fine. Anyway, I was about to stop because I just want to conclude and stop. No problem. It's okay. Then we need to copy this.
Yes, sir.
Yes, sir.
Now, so in general, what we can say is that let's talk about 1D infinite, 1D box, but unsymmetric one, the regular one basically. Okay. Now let's talk about 1D box, but a symmetric one. Okay. Here, wave function psi n is always root of 2 by a sine n pi x by a. Always. Where n starts from 1, 2, 3, 4, blah, blah, blah. However, here psi n is root of 2 by a cos n pi x by a and root of 2 by a sine n pi x by a. This formula you have to use. Cos, remember, but you have to remember, cos is even. It means it is valid for odd. I think this is how you can remember forever. You not even confused. Remember it's opposite. If it's cos is an even function, it means it is valid for only odd quantum numbers people. This is valid for 1, 3, 5 quantum numbers. And since sine is an odd function people, this is valid for 2, 4, 6 quantum numbers people, even quantum numbers. Okay? But tell me one thing, at the end of the day, energy, that is not going to change. Because what will be energy for this n square pi square x square upon 2 m square? Here also it will be n square pi square x square upon 2 m square. Here also it will be n square pi square x square upon 2 m square. That's energy is not going to change people. Okay? Because n is still n. Just that wave function changes. It was 1, 2, 3, 4, 5, 6. But energy corresponding to 1 will be 1 square pi square x square upon 2 m square. Energy corresponding to 2 will be 2 square pi square x square upon 2 m square. Energy will not change. Energy for both of them remains n square pi square x square upon 2 m a square. Is that clear? Is this flowchart distinguish whatever you want to call it summarization? Help you to understand with clarity what is the difference?
Yes, sir.
Yes, sir.
Okay. Others, do you have any questions?
I'm
No, sir.
processing it.
Processing it. Okay. Please ask everyone. Take your time.
Okay, sir.
Okay. Okay. So let's take the break now itself and let's meet at 6:45 sharp. You may leave. Thank you so much.
Thank you so much.
No problem.
Thank you, sir.
No problem. No problem.
Bye, sir.
भी मिलेंगे
अभी आ रहे सर.
हाँ जल्द मिलते हैं. ठीक है. चला. If anybody is starting, let me know. I'll end the session.